Hi guys. So today we're going to look at the last day of our unit on rational functions. What we're going to do today is we're going to take a fraction and actually separate it into multiple fractions as opposed to what we've been doing the past few days where we've been combining fractions together. So some simple examples of this using kind of what you've already learned so far. If you have addition or subtraction in the numerator, you can separate that as long as you keep them both over the same denominator. Same thing over here on the next one. I can separate that into x over 2x plus y over 2x. And if I want, I can even cancel those x's out and make that 1/2 plus y over 2x. Over here on this last fraction, again, if I wanted to, I can separate that and put each one over those denominators. And even if I wanted to, I could simplify those x's. But what we're going to look at today is instead of separating it that way, we're going to see what happens if I separate the denominators and how to figure out what numerators would go with those. Now, just so you know, the answer to this is going to be this problem down here. And just as a review, let's work that out. I'll multiply the left by x plus 1 and the right by x. And that gives me that common denominator. So I would get 3x plus 2 over x times x plus 1. So that means that 3x plus 2 over x times x plus 1 is the same thing as 2 over x plus 1 over x plus 1. So we're going to figure out how to get those numbers. So the first thing that I'm going to do for all of these is factor. Okay, I'm going to factor the denominator. Well, this factors into x minus 3 and x plus 2. So that means that I want to separate this into something over x minus 3 plus something over x plus 2. So the way that I'll separate it, over x minus 3, we'll have something, we'll call it a. And then over x plus 2, I'll have something, we'll call it b. Well, if I want to combine those two fractions together, I would multiply the left fraction by x plus 2, and I would multiply the right fraction by x minus 3. So if I did that, then I would have a times x plus 2 plus b times x minus 3. And that would be, when I combine that together, this would be the new numerator. Well, that numerator needs to be the same as the original problem, which is x plus 7. So in order to solve for these values, there's really two different methods that you can use, depending on which you think is easier. This first method is a little bit longer, but it's a process we're going to need to use for some of these more complicated examples going forward. The second method I'll show you is kind of a shortcut for these specific types of questions. So what I'm going to do is I'm going to distribute. And then I'm going to rearrange it just so those terms that have an x are together. So now, what I have is I have an ax and a bx. Now, we're not actually solving for x. We don't care what x is. I'm trying to solve for a and b. Well, since I have two variables, I need to set up a system with two equations. Well, what I know about ax and bx, if I combine them together, that's my total number of x's, whatever a is and b is. So a and b needs to add up to the total number of x's in the numerator, which in this case is 1. So one of these equations is a plus b equals 1. My other equation I'm going to get from the constants. So 2a minus 3b, it does not have any x's. So it'll never have anything to do with that x in my numerator. 2a minus 3b, though, does need to equal the constant, which is 7. So at this point, I just need to solve this system. We'll go ahead and use elimination. I'll multiply by negative 2. So that gives me negative 5b is equal to 5, and I get b is negative 1. Once I know what b is, I can plug it back in, and I get that a equals 2. So that means my answer to this question, this original fraction would break down into 2 over x minus 3 minus, well, I'm going to do plus, negative, or minus, 1 over x plus 2. All right, the second method is a little bit of a shortcut. It's going to start the same way, though. I'm still going to do a times x plus 2 plus b times x minus 3, and that's still going to equal x plus 7. But to solve for a and b, what I can do here is use elimination kind of at an earlier step. So if I want to eliminate the a here, I can pick a value of x that's going to eliminate a. Well, if I multiply a times 0, it'll be eliminated. the x value that would do that is negative 2. So if I plug in negative 2 for x, I would get a times 0 plus negative 5 times b, and that's going to equal 5. So that means that negative 5b is equal to 5, and b is equal to negative 1. Same answer I got the other way. Well, now I'll do the same thing in order to cancel out that b, I'll let x equal 3. Well, then 5a plus b times 0 is going to equal 10. If 5a is 10, then a is 2. Same answer. All right, so let's try a couple more. If you feel comfortable so far, pause the video and try these, and then we're going to do some more complicated examples after. All right, first step is to factor the denominator. And then I'm going to separate it, and I have to list how I want my answer to look. Now, your A and your B could be flipped, and that's okay, but your final answer is still going to end up the same because your A and B would be flipped. So it matters which one is over the x plus 4 and which one is over the x minus 2. If you change it, you'll still get the same answer in the end, but you have to identify it at the beginning so you remember which one's which. All right, so again, to solve this out, I would do a times x minus 2 plus b times x plus 4, and that should equal my original numerator of x minus 8. Well, the x values to plug in, I would start with 2. That would eliminate a, so I would have 6b equals negative 6. So I'd get that b equals negative 1. All right, another value could be negative 4. That would be a times negative 6 is going to equal negative 12. And I'd get that a equals 2. So my final answer would be 2 over x plus 4 minus 1 over x minus 2. And again, if you flipped your a and b in the original statement, that's fine, but your a and b values in your answer would be the opposite of what I currently have. It's still right, because when you still write it, the one that you write after, the one that you write above the x plus 4 needs to be the 2. All right, so let's go on to example 3. We'll go ahead and factor. That's going to add up to 6 minus 1. So this is going to be a over 2x minus 1 plus b over x plus 3. So to work this out, I would do a times x plus 3 plus b times 2x minus 1, and that equals 4x plus 5. Again, I'm going to plug in the zeros because I think it's a little bit simpler. So I would plug in negative 3 for a. So then that would cancel out my a value. I would have b times negative 7. And then that's going to be negative 12 plus 5, which is negative 7. So I get that b is 1. Then I'll plug in to cancel out b. That would be 1/2. So a times 3.5, that would be a times 7 over 2. 4 times 1/2 plus 5 would be 7. And I'd get that a equals 2. Plug it back into your original. My a was above the 2x minus 1. My b was above the x plus 3, and that's my solution. So what we're going to look at now are a few special cases that are just a little bit harder to do. So the first special case is whenever we have a factor that is squared, or has a multiplicity higher than 1. Now I'm actually changed this from the original example because we can still show this concept with a little bit of an easier example. So I'm just going to rewrite this problem. And I'm going to rewrite it as minus 2x plus 3. All right, so anytime we have a squared factor or a cubed factor or a factor with a higher multiplicity, when I actually break this down into its parts, one of those parts could have x minus 1 in the denominator, or that denominator could have x minus 1 squared. Or again, that denominator could just be regular old x minus 1 cubed. So I need to consider all three of those as possibilities. Now, not all three of those could be in our answer, but if it's not, we'll get a 0 for that value, and it'll make it clear that it's not. All right, now this is, again, a case where it's really important to use our least common denominator, because if I don't use the least common denominator, it's not going to equal the numerator that I have, because the numerator that I have is the fully reduced function based off of that least common denominator. So the least common denominator is the x minus 1 cubed. Well, that first fraction already has 1 x minus 1, so it needs to get multiplied by x minus 1 squared. So I would do a times x minus 1 squared. The middle term has 2 of the x minus 1, so it still needs to get multiplied by x minus 1. C already has the common denominator. So at this point, I'll just do the algebra. And that, again, is going to equal that common denominator. And I'll simplify one last step. So at this point, if you wanted to, the method we talked about with the zeros, you could use that on the first step. I could plug in 1, but you'll notice that's only going to give you the value of C. It's not actually going to give us all of those values. So it's important for us to really be able to do this system method. So in that system method, we have 3 variables, A, B, and C. That means we need 3 equations. One of those equations will be based off the x squared, one of those will be based off of the x's, and one of them will be based off the constants. So the first one is just my x squareds. Well, I have ax squared and then just a 1x squared on the other side. Well, that means that a has to equal 1. Then we'll go on to the x's. Minus 2ax plus bx is going to have to equal negative 2x. That means negative 2a plus b has to equal negative 2. Well, now I already know that a is 1. That means that negative 2 plus b is negative 2, which means that b is 0. Then we go to our last equation. A minus b plus c has to equal 3. Well, b is 0, a is 1, so 1 plus c is equal to 3. C equals 2. Now I know my a, b, and c values. I can fill in my original fractions. So 1 over x minus 1. There is no x minus 1 squared in the denominator because we got that 0. So my only other fraction is 2 over x minus 1 cubed. All right, next one did not print on my slides, so I'm going to rewrite it in there for you guys. So the next one involves our next special case, and that is when we have a factor that doesn't break down into a linear factor. So something like this. So until this point, all of our factors, like the thing that was actually in the parentheses, was linear. So when I break this up, I'm going to have x, and I'm going to have x squared plus 3 in my denominators. But again, until this point, because I've had just first degrees at the bottom, I've only had a constant at the top. Well, now that I have a squared factor in the bottom that can't break down any farther than that, that means the numerator could be linear. So instead of just b, I have to consider that this could be b times x plus c, because it could be a linear factor. Now it doesn't have to be, and if it isn't, then we'll get a b value of 0, but we need to consider it and give that as a possibility. So the way I'll work this out is I'll do a times x squared plus 3 plus bx plus c times x, and that should equal my original numerator. Well, let's do the algebra. Ax squared plus 3a plus bx squared plus cx. And then we can set up our system from here. We'll start with our squared terms. Ax squared plus bx squared. Well, there is no squared on the other side. That means then that a plus b is going to equal 0. All right, on the next one, we'll look at our x's. Cx equals 1x. That means c is 1. Then we go to our next one, 3a, that's my only constant, is equal to negative 3. That means a is equal to negative 1. Well, if a is negative 1, plug it back into the original equation. That means that b is positive 1. Now that I know all my values, I can rewrite them on my fractions. So I get negative 1 over x plus 1 over x squared plus 3. All right, let's do another one that has a quadratic factor. So again, start by factoring the bottom. We'll take out the x. So I have my two denominators. And the second denominator is quadratic, so we're going to call that bx plus c. So I'll multiply a by x squared plus 4. I'll multiply bx plus c times x. So I get ax squared plus 4a plus bx squared plus cx. That needs to equal 3x squared plus 4x plus 4. We'll set up our system, starting with the x squareds. So a plus b is equal to 3. All right, then I look at my x's. Cx is equal to 4x, so c is equal to 4. Then I look at my last one. 4a is equal to 4, so a is 1. Well, if I know a is 1, plug it back in. That means b is 2. That means my equation would be 1 over x plus 2x plus 4 over x squared plus 4. All right, so the next one's kind of tricky because it combines really those last two special cases together. So I have a squared factor. That means I need to consider all of the multiplicities. So x squared plus 2 or x squared plus 2 squared. Now both of these factors, though, what's actually in the parentheses, are quadratic, which means both of these could be linear at the top. So I'll go ahead and use 2 new letters, and then I'm good. The left fraction, to get that common denominator, needs to get multiplied by x squared plus 2, because it already has one of them, and our common factor there is just squared. The cx plus d already has the common denominator, so I'm already good there. And then this should equal the numerator. We can go ahead and FOIL it out. So ax cubed plus bx squared plus 2ax plus 2b and then we'll set up our system. 4 variables, so 4 equations. We'll start with the cubics. Ax cubed is equal to 8x cubed. So that means that a is equal to 8. All right, we'll go on to our b's. Or our squared, sorry. Bx squared. There is no x squared. So b is equal to 0. All right, we'll go on to the x's. 2ax plus cx. So 2a plus c has to equal 13. Well, I already know that a is 8. So c is equal to -3. Then my last equation, 2b plus d, is my constant. There is no constant, so it's 0. If b is 0, d is 0. So my final answer here would be 8x over x squared plus 2 plus -3x over x squared plus 2 squared. So again, this one just combined both those concepts together about having that quadratic in the factor and also having those multiplicities. That's about as hard as it gets. The last one actually looks more complicated than it is. So until this point, all of the factors that we've looked at have had a higher degree in the denominator. And now this is actually a typo. If the degree of the denominator is less, okay, or not larger than the degree of the numerator, then what we're going to do to simplify this to start is actually use division. Because if you remember when we do division, we write the remainder as a fraction over the divisor. So that'll be the only fraction that we have left over. So if I do my division, I start with 2x, I multiply, I can subtract. So this is going to be -x squared minus 3x plus 7. Then we'll go through again. I'll get -1. I'll subtract. I get -2x plus 5 as a remainder. So the way that we write this, remember, it's 2x minus 1 plus -2x plus 5 over x squared plus x minus 2. So now we've already done half the work. This part's done. All I need to do now is break down that last fraction. And that last fraction is really pretty simple. That's very similar to the ones that we saw at the very beginning. So that factors into x plus 2 and x minus 1. So to solve this, I would do a times x minus 1 plus b times x plus 2. That's going to equal my numerator of negative 2x plus 5. And since this one's pretty simple to plug in zeros, I'll just plug in zeros. I'll plug in 1. That would give me 3b equal to 3. I get b equals 1. I can plug in negative 2. So I get negative 3a is equal to 9, and a is equal to negative 3. So my total final answer here would be 2x minus 1 minus 3 over x plus 2 plus 1 over x minus 1. All right, so that is everything for the unit for rational functions. So again, a lot of operations here at the end and a lot of algebra. But again, just review any of the other videos that you may need before our test coming up.